Hello and welcome to Toddcast number 58. We're starting chapter 19, but truth be told, where 19 starts and 12 ends, it's just a blur because we're going to do very similar things. We spend a lot of time talking about oxidation reactions to generate carbonyls, talk about reduction of carbonyls to alcohols. So we've covered a good amount of the foundation of it already. And so this time we'll add a few reactions. We'll revisit those, some of those oxidation reductions, and then we'll just consider like the carbonyl in general, just the carbonyl basically as an electrophile. And eventually we're going to get into the carbonyl's alpha proton, so the carbon right adjacent to the carbonyl, how those can get involved by deprotonating that and how that those sorts of reactions can occur. But for now, we're going to start with a review of aldehydes and ketones. And there's a good chance that we got about 7 more of these podcasts, 6 to 7, that'll cover the end of this chapter. But I apologize in advance for some of the review that will be in the remaining ones. Okay, so let's start with just concept of what an aldehyde is. So an aldehyde, carbonyl compound, so it has C-double-N-O with an H. Doesn't have to have 2 H's. This one does, but this is methanol, more commonly known as formaldehyde. Fun fact, formaldehyde doesn't really exist in that form. You typically find it in a cyclic form where all these lines represent hydrogens. So formaldehyde prefers to be in a 4-bond to carbon all sigma arrangement. So you typically do not see individual methanol, individual formaldehyde, but just random fun fact. But it does, in essence, form this type of structure at least 1, maybe 2% of the time. Okay, so methanol, if you have carbons on both ends, it's known as acetone. So just want to emphasize that anytime you see this group right here, let me go ahead and color coordinate this. This group is the ace group. So it is acetone, acetaldehyde if it's an H, acetic acid if it's an OH, acetic anhydride if there's an O, and then another carbonyl and an R group. But the key thing is this is that. Hence, when you in bio come across something called acetyl-CoA, this is your acetyl group, 2 carbons with a carbonyl, and that one's attached to a sulfur connected to a coenzyme A or CoA. But the key thing here is this group right here, the ACE group, acetone. In this case, a common name. You're expected to know both for something that common in chemistry. Okay, a little more complicated, more, I guess, more complex structure, but vanillin, flavoring agent found in vanilla items, has an aldehyde at this end. It's a conjugated aldehyde because of the benzene ring that's connected to it. And then finally, something like this, where it's an alpha-beta unsaturated ketone. So this isn't necessarily a ketone by itself. It still has a ketone functionality because it has R groups, but I emphasize the fact it's an alpha-beta unsaturated, meaning 1 away we call the alpha carbon, 2 away we call the beta carbon. You have a double bond, meaning unit saturation between the alpha and the beta carbon, so alpha-beta unsaturated ketone. Note that this is also an alpha carbon. This is also a beta carbon because it's 2-way. This is also a beta carbon, but the unsaturation is here. Okay, and if you recognize it, something we'll get into very quickly here is this has a grand total, this being carbone, of 1, 2, 3, 4, 5 carbons. See if that makes any significant impact on what we know. And here we have 1, 2, 3, 4, 5 carbons as well. So if I broke it off here and here, I'm going to get what's known as isoprene units, 5 carbon fragments with a skeleton of 4 straight carbons, 1, 2, 3, 4, and a group coming off the second one, 1, 2, 3, 4, with an alkyl group coming off the second one. And so we'll go into more details of what exactly that means. as we go through it, but know that this is a naturally occurring 10-carbon lipid or hydrocarbon. And I should say, because it has oxygen in it, it's a hetero-involved hydrocarbon, but very, very common that we have compounds that are built from 5, 10, 15, 20 carbons in this isoprene connected fashion known as terpenes. Okay, just some fun facts we'll get into. So the common biological ones to worry about. Again, the term terpene will pop up quite frequently in the early part of this lecture. But transretinal may sound familiar because this is what's part of rhodopsin you find on the surface of your retina in the form of rods. So rods detect light, cones detect color. And so light, more like intensity. If light comes in and strikes that pi bond right there, it can break the pi bond, which turns it into a pair of radicals, which are stabilized. Because it's now a sigma bond, this can freely rotate up to cis or back to trans, cis to trans. So because of the rotation possibility, this is kind of like a gate where it might block some site, but if this rotates out of the way, then once it's out of the way and sticking up here, then the calcium has a free path to bind whatever receptor. When it binds a receptor, it sends a signal to the optic nerve that this rod has been activated, and it processes it. Depending on how your eyes are functioning within the light, it may process every single calcium that reaches the receptor. That would be called night vision, where you have to detect everything you can, every possible photon. But usually in the course of a day, if you're out in somewhat bright external light, maybe 5 of them have to be struck before finally your optic nerve or the brain processing the optic nerve signal will say, yep, there's some light going on there. So the point being, this compound is part of a bigger compound called rhodopsin when it binds to a protein on the surface of the retina, and it's used to detect light. Note that I use green light because that is what we actually see. That's why night vision goggles or night vision, night cameras, any device, you'll notice a green hue associated with it. It's because of this green light functioning with our rods. Okay, also estrone, you'll notice this is a steroid, 6-member ring, 6-member ring, 6-member ring, and a 5-membered ring. There's usually an R group here and here and some R group coming off. So this is kind of a more simplistic one, but it's part of the estrogen grouping. So estrogen is actually not a single compound, but basic group of multiple compounds that make up the hormone. We have 4-hydroxytransnona now, which, interesting thing, if you look it up, you'll find that this is a degradation product that happens after we start to age. So this is one of those molecules. Toxic is maybe not the right word I'm fishing for, but the presence of this in our body generally is equated to something breaking down or something malfunctioning. So this metabolite, if it's in high enough concentration, generally is indicative that starting to age or starting to break down wherever you're detecting it. Testosterone, very similar to estrone, in that it's a sex hormone. Same steroid ring structure. Notice the 2 CH3s instead of just 1. And again, less complex coming off, very simple molecule. But these are messenger molecules. Hormones are released by glands, travel through the body to some site where they get detected. Okay, so I'm pretty happy with how these are turning out. As I mentioned earlier, terpenes and terpenoids, just going to briefly address it. It's one of those topics that chemists used to make a really big deal about because when we first started doing a lot of natural product synthesis, when we decided we were better than nature, that we could design things better or synthesize things better than the natural pathways, we tried to make a lot of quote unquote natural products, take something isolated in nature and then figure out how to synthesize it. Most of our synthesis started from, as I mentioned before, a 5-carbon species known as isoprene, 1, 2, 3, 4, with a methyl group. So I'm just going to number this just for reference in the future, but 1, 2, 3, 4, and then a methyl coming off of 2. So pay a large amount of attention, carbon 2, because it has 3 bonds to carbon. And so we normally talk about isotopic labeling the following atom, but sometimes you can actually just do functional group labeling, if you will. So the one with the methyl is a carbon 2 in the original fragment. So I have the numbers that have popped up. So let me go ahead and erase my yellow. And I want to start looking at more complex compounds. So these isoprene units can combine. They typically combine 1 to 4 of another species or 4 to 1. So in other words, they connect head to tail. So if I call this the head, it's going to connect to a tail of another one. So another tail will kick in. So if I'm numbering this right, I want to always recognize my 2's first. So there's a 2, that's a methyl, and here's a 2. So if I count back, I'm going to assume that's a 1 because it's connected to the other end. 3, 4, and a methyl. On the other end, if this is my 2, then my 1 is probably there. 3, 4, and a methyl. So sure enough, there's your 1 to 4 head to tail connection. How it happens, we'll go into a little bit of detail, but these are common hydrocarbons found in the body. And unlike hormones, a lot of these make up pheromones. You don't have the same signaling. You don't have the same, I should say, steroid ring structure, but used for messenger molecules, be it in the body, but most often messenger molecules from plants to, I guess, neighboring plants, to animals, to whatever. So these tempting smells we smell, we eat the fruit, we eat the leaves, we consume the plant, and this signal molecule gets us to do it as such. And in exchange for this wonderful flavor that we get, we take their seed and plant it somewhere else for them. So this signaling molecule, and I'm just going to loosely call it a signaling molecule, is a terpene, meaning it's made from 5 carbon fragments. So again, let me erase what I've put, but notice the 2's and the methyls. So always easy to identify the 2 carbon in the fragment. And again, the 2 is connected to a 1, a 3, and a 4. 2 is connected to a 1, a 3, and a 4. So there's the numbering we just did earlier, I did before I erased. So that's my new bond. So if I want to pay attention to that, those are my 2 fragments. And kind of cool and kind of ironic that I picked the same colors, red and blue, that I just did circles with. Okay, more complex. So again, this is mentioned earlier, retinal and transretinal at that, but I'm just going to call it retinal for now. And I want to see if that is actually a terpene or an isoprene built compound. So I'm going to start with where I see methyls. So that's a 2, that's a 2, that's an M, that's an M. One of these must be a 2, one of these must be an M. It's going to get me a little confused. And actually, let me do this is a 2, there's an M. So have to figure out how this thing connected. So I'm going to say, let's count from this end. That looks like it would be the easiest. We have a 4, 3, 2, 1. So that's a new bond. 1 is to 4, 3, 2, 1. That's a new bond. So far, so good. 4 in a row with methyl off 2. 4 in a row with methyl off 2. This is where I'm going to get a little bit tricky. So this is a 4. This would be a 3. So something really weird is happening on this one. So I need to figure out how the heck that can be. So if this is a 1, then we made some odd connection here. So this is still working right here. But this last one, I must have done something off. So I need to go back and see how my numbering goes. So if I end up numbering this way instead, so let me undo, and unfortunately it's going to do away with all those bonds I did up there. But I now know that this 2 must have something to do with this other one. So again, 4, 3, 2, 1, 4, 3, 2, 1, 4, 3, 2, methyl 1. Let's see if this is any better. So this group would be a 4, 3, 2, 1, and methyl. So sometimes you got to mess it up to get it right. So there are my cuts. There's 1 isoprene fragment, 2, 3, and 4. So this is basically an exercise in analyzing the skeletons of a structure. So let me go ahead and undo what I've drawn in and let these kick in. So again, you identify what you can. So what I can identify are the 2's with a methyl, 2 with a methyl, 2 with a methyl, 2 with a methyl. Now, I numbered the wrong way first, and that's fine. Experimentally, it's fine, but starting from this end, going backwards, 4, 3, 2, 1, check, 4, 3, 2, 1, check. For this end, it'd be 4, 3, 2, 1 with a methyl. And apparently I have 1, 2, 3, 4, and that's what I meant. And so you don't always get the connection you expect. So this connection was 4, 3, 2, 1 there, and there's my connection from before. So a 1 to 4 check, a 1 to 4 check, a 1 to 4 check, but this weird 2 to 3, not very typical, not usually what we see, but still a terpene, still built from those fundamental fragments. Okay, so I would recommend stopping the video and trying this on your own, seeing if you can figure it out. I'm going to just go ahead and solve it, so hopefully you stopped it and tried. But again, 2 and 2, I'm going to arbitrarily call that the methyl and this the 1. I'll arbitrarily call this the methyl. And I don't know which one to call 1, so I'm going to make some sort of judgment call in a second. That's a 3. If I choose to call this one 4, that's still going to work out for me. That makes this a 1, a 3, and a 4. The new bond is right here. But I could also have done this as 4 and made this 1, 2, 3, 4 and cut that way. So it doesn't always work cleanly. So again, the ones that are obvious are the 2 and the methyls. And then if I go 1, 2, 3, 4, break that way, or 1, 2, 3, 4. So this one's a little bit odd, is my new bond is here and here. It could have also, as you saw, been there and there. So, I mean, it's, again, judgment call on this, but figuring out what the fragments are. So this is called a monoterpene because it's 10 carbons. This would be called a diterpene because it's 20 carbons. Not that I will ever ask you that sort of thing, but just recognizing the skeletal connections is key. This one, good luck. This is actually really confusing. So here's my 2. Here's my methyl. Here's my 2. Here's my methyl, which means that's got to be a 1. How you connect them from there is completely a scatter plot. So I have my 1, 2, and my methyls. So we can just make a educated guess. So we'll call this one 1. This one has to be a 3 because it's connected to a 2. If I call this a 4, then this other one will be 1, 2, methyl, 3, 4. At least one way, but it can also, I can number them the other way. So let's see if this is the way we did it. Sure enough, it was. It doesn't have to be. There's multiple ways to do it. Key thing I care about is, can you make the connections? Okay. On this, it's important to be able to recognize what the fragments were, what the 4 and the 1 were, and we might get into a little more detail of exactly how these are formed biologically, but we haven't gotten into the chemistry you need to form them synthetically, called the Diels-Alder reaction. So I'm just going to leave this as an interesting bio piece of tidbit that notice this became an aldehyde, this became a ketone, this is a ketone, this is an aldehyde. The original isoprene typically gets turned into an O with a phosphate or pyrophosphate actually. Phosphate can leave an alcohol, which can oxidize up to the carbonyls. So carbonyls are very, very common in terpenes. Okay, so looking a little more carefully, citral. If I want to figure out how this has happened biologically, I just need to do a count. I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 10 carbons. The plus signs equal the number of new bonds. So 5 plus 5 equals 10. 1 new bond. So there's my first 5. There's my second 5. And again, carbon 2, methyl off of it. Carbon 2, methyl off of it. 3, 4 for the end of the chain. So 1 must be here. There's my new bond. So it breaks into those two. So my 5 plus 5, each plus sign represents a new bond that must be made. So this one, 15 carbons. So in that case, the calculation would be 5 plus 5 plus 5 equals 15. 2 plus charges, 2 new bonds. Again, methyl, methyl, and methyl. Carbon 2, 2, and 2. This must be a 3, 4. This must be a 1, therefore 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Can easily find the connection when it's linear. From those weird ring systems that mess with me. So they're my 2 new bonds. So it would break into that. And then camphor that we just did, again, just to emphasize, this is 10 carbons. So 5 plus 5 means 1 new bond for the ring, or for the connection, 5 plus 5. But then I have 1 ring and I have 2 rings. So 1, 2, 3 new bonds have to form. So bicyclic. For every ring, there's 2 rings altogether, so bicyclic. 5 plus 5, 1 bond for the plus 5 plus 5, and then 1 for each of the 2 rings. As we did earlier. My bonds are 1 to 4 is expected, head to tail, 4 to 3 to close the 6-member ring, and then this weird 2 to 2 bridging connection. Okay. Not much else to terpenes other than recognizing connect the dots. It's been tested pretty heavily on the MCAT over the past, well, I'm going to say approximately 7, 8 years. And it's because it's on a lot of their practice exams that I'm guessing whoever writes tests will base it on those practice exams. So it's not a bad topic to know the skeletons. And then just one piece of information is usually 3 acetyl-CoAs, 3 2-carbon fragments come together to make 6 carbons. It undergoes decarboxylation, the loss of CO2 to become 5 carbons, and then turns into that unit we just saw. This is known as isoprene. That's what we deal with in OChem. But a lot of times what you're dealing with will be something like this or something like this with a, I'm going to call it a pyrophosphate. So that just represents an O with a phosphate and a phosphate. So pyrophosphate for the energy, these 2 combine. So this is the biologically active form of that compound. Okay, well, this is 1 Toddcast down. Hopefully this seems okay for you. And I will see you at the next Toddcast. Thanks. Bye.